University question on design of plate girder. This is for JNTU for the year November 2020. And this plate girder design involves calculation of bending moment due to UDL comprising of 2-point loads and then designing the section. This is the question. Design a plate girder for a simply supported bridge deck with a clear span of 18 meters. The dead load including self weight is 20 kilonewton per meter and imposed load is equal to 30 kilonewton per meter. Therefore, the total dead load is 20 plus 10, 30 kilonewton per meter. That is what is written here. Two moving loads of 100 kilonewton, each spaced at 2 meter apart. And that is marked here, 2-point loads, 100 kilonewton. Assume the top compression flange is laterally restrained and prevented from rotating. That means full stress can be used. Fy can be taken for calculation of bending moment. If the beam is not laterally restrained, then we have to calculate FBD depending upon the L by R ratio of the beam and also H by thickness of the flange ratio. And here FBD need not be calculated. Fy can be taken for calculation of bending capacity. That is the significance of lateral restraint of the beam. Design this as an unstiffened plate girder. This is very important. We have to design this as an unstiffened plate girder. That is, the web should be capable of resisting the shear force on its own without any stiffeners. No stiffeners should be provided. This is one important point. Now, we will calculate the bending moment for two load cases. Here, the system is subjected to uniformly distributed load plus a set of 2-point loads. For calculation of maximum bending moment due to 2-point loads, 1-point load should be placed at a distance of S by 4 from the midspan. Here, the distance between the 2-point loads is 2 meters. If X is the distance between the 2-point loads, here it is 2 meters. S by 4 is 0.5 meter. So 1-point load should be placed from the midspan at a distance of S by 4, 2 by 4, that is 0.5 meter. This corresponds to the maximum load created by the point loads. By the way, the total span, the effective span is taken as 18.6 meter. 18 meter is the clear span. Let us assume the bearing width is 600 mm on either side. Center to center of the bearings is now 18.6 meter. You can take 18.6 or 18.5. So out of 18.6, this 0.5 is the distance of 1-point load. Therefore, 18.6 divided by 2 is 9.3. Out of 9.3, this 0.5 is gone. Therefore, this is 8.8 meter. And the other point load is at a distance of 1.5 meter because the distance between the 2-point loads is 2 meter. So out of 9.3, 1.5 meter is gone. Therefore, this distance is 7.8 meter. This is one case for calculation of maximum bending moment. This case will give the maximum bending moment due to point load. But we also know that maximum bending moment due to uniformly distributed load will occur at midspan. So for getting the maximum bending moment at midspan, we have to place the loads differently. The load distance between the two loads is 2 meter. These two loads should be placed equidistant from the midspan. So from the midspan, both the loads are placed at a distance of 1 meter. The half the span is 9.3 meter. 1 meter is distance of the point load from midspan. Therefore, this is 8.3 meter. This is 1 meter, 1 meter. These are the two load cases we have to investigate for calculation of bending moment. This is first case where one point load is placed at a distance of x by 4, that is 0.5 meter from the midspan. In the second case, both the point loads are placed equidistant from the midspan. For these two cases, we have to calculate the maximum bending moment. Here, the maximum bending moment occurs under the load. Please note, here the maximum bending moment occurs under the load. Now, first we have to calculate the reaction. This reaction can be calculated, let us say RA. This reaction can be calculated by taking moment about this support. This can be done by the calculator operation with M plus facilities, memory plus facilities. First, you can calculate the reaction at this end due to uniformly distributed load. Then you can calculate the reaction due to this 100 kilonewton load. This is load divided by the span, 100 divided by 18.6 into distance from another support. We want to calculate this load. The distance from another support is this much, 7.8 plus that is 18.6 minus 8.8. That is 7.8 plus 1.5, 8.3, 8.8, 9.3. So 7.8 plus 1.5, that is 9.3 plus 0.58, 9.8. So due to this 100 kilonewton load, this reaction can be calculated. It is 100 kilonewton divided by span 18.6 into distance from another support 9.8. Then similarly, due to this load, the reaction at the left end can be calculated. That is load by span 100 kilonewton divided by 18.6 into distance from another support 7.8. Any load, the reaction is given by load divided by span into distance from another support. You want to calculate this reaction. This reaction is equal to load 100 kilonewton divided by span 18.6 into distance from another support 7.8. Due to this 100 kilonewton, the reaction at left end is given as 100 divided by 18.6 into 7.8. So this reaction at left end can be calculated with the calculator operation with the M plus facility. Now my aim, let me tell you, it is not to do away with classroom teaching. Classroom teaching is anyhow essential. It is very much important. This is just to supplement the classroom teaching, and it will also serve as a matter of reference. So these calculations are done with the specific intention of making it presentable in a compact form, say with one A4 sheet. The whole calculations will be given in one A4 page. So the calculations are very concise and very brief. That is the very basic objective of this. So this is the first load case. Now let us calculate. Having calculated this reaction, we can calculate the bending moment which happens under the load for giving the maximum value. So this reaction 373.6 under the load distance 8.8 minus this uniformly distributed load 30 into 8.8, that is the total load in acting at a distance of 8.8 by 2. So this is the bending moment under the load, and it comes to 2126 kilonewton meter bending moment under the load. Now let us see what is the maximum bending moment for the second load case. For the second load case, this reaction is 379. kilonewton. Here the reaction calculation is somewhat simple because it is just the total load divided by 2. 100 plus 100, 200 by 2 plus 30 into 18.6 by 2. That will give the one value of one reaction. Here we have to calculate the bending moment at the midspan. Now 379 is the reaction. The midspan distance from left support is 9.3 meter. 379 into 9.3 minus 30 into 9.3 load acting at a distance of 9.3 by 2, 30 into 9.3 square by 2 minus 100 into 1 kilometer. These 2 point loads are placed at a distance of 1 kilometer from midspan section. This gives to 2127 kilonewton meter. Both are very close. So second load case is higher by 1 kilonewton meter, just higher by 1 kilonewton meter. So this case governs. Second load case governs. And this question is given about 28 marks out of 100 marks. That means somewhere about 35 to 40 minutes are allotted for this university question. So that also should be kept in our mind. Our aim should be to finish off the design. It should be safe. That should be our primary aim. We need not aim for optimization of the section or we need not aim to make any ideal design. Now, let us provide the depth of the plate girder as 1000 mm. It is just an approximation. When for long span bridges, you can assume the depth as 1 meter to 1.5 meter, anywhere about 1 meter. I am deliberately assuming this as 1000 mm so that if the depth becomes more, the section becomes slender, it will call for stiffness. So I am deliberately assuming the depth on the lower side 1000 mm. For long span bridge girders, the depth will be in the range of 1 meter to 1.4 meter or 1.5 meter. Here I am assuming this depth of the web as 1000 mm. MU, we have to apply the load factor. We have calculated the maximum bending moment 2127 kilonewton meter. Apply the load factor of 1.5. 2127 into 1.5, 3191 kilonewton meter. This is the bending, ultimate bending moment. Our section should have the bending capacity which is higher than this value. That is the aim. Now let us find out approximately what is the flange area. The total bending moment is the equation for approximate flange area. 3191 is bending moment in kilonewton meter. For getting it in Newton meter, multiply this by 10 power 6. I have told the web depth is 1000 mm. So the lever arm will be 1000 plus thickness of the plate. But approximately the lever arm can be taken as 1000 mm. That is why I have written this approximation. So bending moment by this lever arm will give the compression in the flange. This is bending moment and depth of the web. Depth of the web is taken as the approximate lever arm. Actually, if flange thickness is 1000, the flange thickness is 32 mm, then the lever arm will be 1032 mm and it is not 1000 mm. If the flange thickness is 25 mm, then the lever arm will be 1000 plus of the thickness at top, of the thickness at bottom, that is 1025 mm. But the lever arm is approximately taken as 1000 mm. And this moment, this divided by lever arm will give the compression in the flange. This we have to divide it by the stress for getting the area. Fy is 250. Material safety factor is 1.1. So the stress is 250 divided by 1.1. That 1.1 goes to numerator. This force divided by the stress gives the area. Multiply this by the material safety factor, because 250 by 1.1 and this 1.1 goes to numerator, and add another 25% extra. That is why I multiplied by 1.25, so that it passes through all the tests such as deflection, shear, etc. So this is giving to 17,550 millimeter square for one flange. Let us provide 32 mm thick plate. Once you provide 32 mm thick plate, this width should be fixed such that flange area is more than 17,550 millimeter square. I have provided 600 mm as the width of the flange and 32 mm as the thickness of the flange. So the flange area 600 into 32. That should be more than the approximate flange area which we have calculated as 17,550 millimeter square. So this is the section we are providing. Now let us calculate whether flange is buckling or not. This overhang of the flange, that is 300 by minus 8. 300 is half the width. 600 by 2 is 300. 8 mm is, now let us assume the thickness of the web as 16 mm. We are assuming this thickness of the web as 16 mm, so that D by T ratio 1000 by 16 becomes 62.5 and it is less than 67. Therefore, there is no web buckling. Stiffeners are not required. Stiffeners are not required. Another advantage is once it is less than 67, the shear stress can be taken at full value. We need not calculate the allowable shear stress. If this is more than 67, we have to calculate the allowable shear stress. That is somewhat cumbersome. It is not possible to complete the working within the time allotted. See that D by T ratio is kept less than 67. 1000 mm is the depth of the web. Provide 16 mm thick plate, then D by T ratio comes to 62.5, which is less than 67. That means full stress can be taken for the shear stress value. Now, B by TF ratio, 300 minus 8. This 8 mm is nothing but half the thickness. So this is the overhang divided by 32. Thickness of the plate, flange plate. 300 minus 8 is the overhang, 32 is the thickness of the flange plate. Ratio is 9.1 less than 9.4, compact. There is no web buckling. There is no web buckling and the section is compact. The flange is compact. The flange is compact. D by T ratio is 62.5. In fact, web is plastic, but the section classification is immaterial. If flange is compact, web is plastic, then the section is called compact section. Lesser of the two we have to take. Anyhow, that is immaterial. What is significant is there is no web buckling. D by T ratio is less than 67. There is no flange buckling because the ratio is less than 9.4. Now let us calculate the properties of the section. ZP, modulus of section, plastic modulus of section. This is the sigma of A1, A into Y bar. The flange area you take 600 into 32 mm. This is one flange area. You have to take the moment about the neutral axis. Here at the neutral axis at the mid depth of the section. What is the arm distance for the flange plate? It is acting at a distance of 16 mm from top. So 1000 mm is the depth of the section. Half the distance is 500 mm. 500 plus 32 by 2, 16 mm. This flange area is concentrated at a distance of 516 mm from the mid depth. So the area is 600 into 32. Y1 is 516. There are two flanges, therefore this factor 2. This is for the flange areas. Now for the web area. Web area, you divide this into two portions. Top portion 500 mm by 16 mm. Bottom portion 500 by 16 mm. 500 by 16. This is area. And what is Y bar? Y bar is it is concentrated at a distance of 250 mm from the neutral axis. 500 is of the depth. Half of the depth is 250 mm. And similarly for the top portion and bottom portion, so you have to multiply by 2. Area is 500 into 16. Y is 250. There are two areas, one at top and one at bottom, multiplied by 2. This gives to 23.81 into 10 power 6 millimeter cube. This is ZP, plastic modulus of section. Let us calculate the other property, IXX, that is moment of inertia. Moment of inertia of the web is BD cubed by 12, 16 mm B, D, 1000 mm BD cubed by 12. This is one term, plus. What about the moment of inertia of the flange plate? Moment of inertia of the flange plate, we have to ignore on its own axis. We will calculate the moment of inertia of the flange plate about the neutral axis only. Moment of inertia of the flange plate about its own axis, we will ignore. Now it is 2 into 600 into 32. 600 into 32 is the area into h square. H square is the moment of inertia. A is 600 into 32. H, the flange area is concentrated at a distance of 16 mm from top. From the neutral axis, the distance is 500. Therefore, 500 into 16, 516. H square 600 into 32 area H square 516 square. There are two places, therefore 2. This is the moment of inertia of the flange plate about the neutral axis. Moment of inertia of the flange plate about its own axis is neglected. It is small. So this is giving a value of 115.5 into 10 power 8 millimeter power 4. Now we have to do 3 checks here as required. One is bending capacity, shear capacity, and check for deflection. Apart from that, we have to design this weld also. Weld between the web and the flange plate. Now, what is the bending capacity? Bending capacity, M is equal to Fz, the famous equation. F is 250 Newton per millimeter square. Material safety factor is 1.1. Therefore, 250 divided by 1.1. M is equal to F into Z. 250 divided by 1.1 is the value of Fy by 1.1. Multiply this by ZP. ZP is already calculated 23.81 into 10 power 6. This whole thing will give the bending capacity in Newton millimeter. And let us calculate the bending capacity in kilonewton meter. So you divide this by 1 by 10 power 6. Now we are getting the moment capacity as 5411 kilonewton meter. This is greater than the factored bending moment of 319 kilonewton meter. Therefore, it is okay from bending moment capacity consideration. Bending capacity is higher than the factored bending moment. Bending capacity is 5411 kilonewton meter and factored bending moment is 319 kilometer. It is okay. Now let us calculate the shear capacity. What is the maximum shear force? Shear force is 379 kilonewton. We have to apply the load factor. 379 into 1.5. This is the factor shear 569 kilonewton. And shear capacity is equal to shear stress into web area. What is the shear stress? 250 by root 3. 250 is Fy. Fy by root 3 is the allowable shear stress. There is no reduction because there is no web buckling. The D by T ratio of web is less than 67. Fy by root 3 is the full value of the allowable shear stress. Fy is 250 by root 3, full value of the allowable shear stress. Apply the material safety factor 1.1. This goes to the denominator. This is the allowable shear stress into the area of the web, 1000 mm into 16 mm area of the web. This gives the shear capacity in Newton. Divide this by 10 power 3 so that you will get the value in kilonewton. This gives the value as 2099 kilonewton. This is higher than the factored shear force of 569 kilonewton. Therefore, the section is okay from shear consideration. Now we will check for deflection. The span, effective span is 18,600 mm and allowable deflection is L by 300, that comes to 62 mm. Now the deflection should be calculated due to point loads as well as the uniformly distributed load. First, we will see what is the deflection due to uniformly distributed load. The factor is 5 by 384 for uniformly distributed load, 5 by 384. What is the total uniformly distributed load? It is 30 kilonewton into 18.6 meter. 13 kilonewton per meter into 18.6 meter. This is the total load. Convert this into Newton, put 10 power 3. So this is the total uniformly distributed load, into L cube. Please note it is L cube and not L power 4 because this is total uniformly distributed load, When it is total uniformly distributed load, the factor is L cubed and not L power 4. Put what is L? 18,600 millimeter cubed divided by E. E is Young's modulus 2 into 10 power 5 Newton per millimeter square. Moment of inertia 115.5 into 10 power 8 millimeter power 4. So this term gives the value of deflection due to uniformly distributed load. Then you are having 2 point loads which are placed at a distance of 1 meter from the midspan. Let us assume that both the loads are acting at the midspan. This is just an approximation. We can't keep on calculating the deflection based on the exact method. Then that itself is a project by itself. So both the point loads are assumed to be acting at the midspan section. So the total point load is 2 into 100. Total point load. Multiply this by 1000. You are getting the value in Newton. This is total point load. Factor is L cube, that is 18,600 cubed, 18,600 millimeter. And what is the deflection factor? It is 1 by 48. EI 48. E 2 into 10 power 5. I 115.5 into 10 power 8. This term gives the deflection due to point load. The total deflection is coming to 31.8 millimeter, which is less than 62 millimeter. It is not meter. 31.8 millimeter. This is not meter. 31.8 millimeter less than 62 millimeter. I'm sorry, this is not meter. This is millimeter. 31.8 millimeter less than 62 millimeter. Now let us design the weld. We will provide the weld between the web and the flange like this. This is 12 mm weld. This is 12 mm weld. Here also 12 mm weld. Here also 12 mm weld. We will provide the weld with intermittent weld. What is intermittent weld? The weld will be done for a distance of 150 mm. Then there will be a gap of 150 mm. Then again the weld will be done for 150 mm. Then there will be a gap of 150 mm. And the notation is like this. 12 mm weld for the near side as well as the far side. Suppose this, if you take this notation applied here, this is near side weld, this is far side weld. Both the sides, the weld is 12 mm. Both the sides, the weld is 12 mm. 150 is the length of the weld. Gap is shown in the bracket. This is also 150 mm. 150 mm length of the weld, and then 150 mm gap, and then 150 mm length of the weld, 150 mm gap. This is how the welding is assumed. Now we have to calculate what is the shear force coming on this weld and what is the capacity of the weld. Let us take one weld strip of length 150 millimeter. Now, what is the influence area for this weld 150 millimeter? Whatever shear force is coming at this weld strip will be taken by this plus this distance between the two weld length is 150 mm. Half of this distance is 75 mm. Similarly, on this side, another 75 mm. So, if you take one weld strip of 150 mm, the influence length is 150 mm plus 75 mm from left hand side plus 75 mm from right hand side. So, the influence length of one weld strip is 300 mm. 75 mm is nothing but half of the gap. Gap is 150 mm. Half of the gap is 75 mm. The influence length is 150 mm. Weld strip length plus 75 mm on left hand side plus 75 mm on right hand side. The total influence length is 300 mm. Now let us calculate the weld shear force which is acting on weld strip, that is 150 mm length. What is the horizontal shear stress? Horizontal shear stress is FA y bar by IB. F is 569 kilonewton. Multiply this by 10 power 3 to get it in Newton. A y bar, what is A? You have to consider the area up to the point where you are calculating the horizontal shear stress. We are calculating the shear stress at the weld point. You have to consider the area from top up to the point where you are calculating the shear stress. That means this flange area will be considered. You are now considering the weld between the flange and top of the web. So you have to consider only the flange area. Flange area is 600 into 32. Area Y bar is 500 of the distance plus 16 mm, 516. So F is 569 into 10 power 3. Area is 600 into 32. F A into Y bar is 516 mm. It is not 516. It is not 576. It is 516 mm. Okay. It is not 576. Y bar is 500 plus 16. 500 plus 16. It is 516 and not 576. It is 516. It is not 576. I'm sorry. It is not 576. It is 516. I 115.5 into 10 power 8. B breadth of the web 16. This is the stress. And what is the area? Area influence area is 16 mm. Thickness of the web into length of the web 300 mm influence length. Stress into area. Stress is AY bar by IB. Area is breadth into influence length 16 into 1300. The whole thing comes to Newton. So divide this by 10 power 3. You will get it in kilonewton. It is 146 kilonewton. Let us calculate what is the capacity of the weld. The capacity of the weld is Fu by root 3. Fu by root 3 is the allowable stress for the weld. Fu is 410. Please note. Fy is 250 Newton per millimeter square. Fu ultimate stress is 410. 410 by root 3. Fu by root 3. And assume that the weld is done at site. Apply the material factor of safety as 1.25. 410 divided by root 3 into 1.25. Okay, this is the material factor of safety. Fu 410 by root 3. Material factor of safety 1 divided by 1.25 into area of the weld. What is area of the weld? Thickness of the weld. What is thickness of the weld? We have provided 12 mm. 12 mm means effective thickness, throat thickness is 12 into 0.707. This is thickness of the weld. And what is the weld length? 150 mm on one side. Then what about the other side? So multiplied by 2. 150 into 2. This is the stress. This is the material safety factor. Stress into area. Area is given by throat thickness into length into 2 because it is welded on 2 sides. The whole thing will give the value in Newton. Divide this by 1 by 10 power 3. It will be 482 kilonewton. This is greater than 146 kilonewton. Therefore, the section is safe. So the longitudinal elevation is this. This is the flange plate. This is the flange plate. This is the web plate. And this is the weld detail. 12 mm is the size of the weld. 150 mm is the length of each weld strip. Gap between the two weld strip is also 150 mm. This is not drawn to scale. Weld length is also 150 mm. Gap is also 150 mm. And what about the cross section? Flange plate is 600 mm by 32 mm plate. Web plate is 1000 mm by 16 mm plate. This is the design, completion of design. This will be uploaded shortly in my website, rgnsite.wordpress.com. Please note, https://rgnsite.wordpress.com. https://rgnsite.wordpress.com. This contains 500 university questions on structural analysis, matrix methods, strength of materials, RCC design, steel design, about 500 university questions. The download is free, and you can also visit my YouTube RGN class. My channel name is RGN class. If you visit my YouTube, you can listen to my other lectures. My channel name is RGN class. Please visit my website where the download is free for 500 university questions and answers. Thank you.